In this video, we're going to study Proposition 1.2 in the Classical Liberal Arts Academy's Classical Geometry course. To prepare for this lesson, you should know all of the definitions, postulates, and axioms required in Book 1 of Euclid's Elements, and you should always also make sure that you've mastered the study of Proposition 1.1. And I want to share a document that I prepared and have made available on the course page. This is a complete summary of all of the definitions, axioms, and postulates, as well as all the propositions which we're going to be studying for Book 1. And this will be an extremely helpful resource for a reference sheet as you work through the propositions. So if you go on the course page, I believe I put a link to this document where you can print it on lesson 1, but otherwise it's on the course page, and I posted today. Today is October 20th, 2020. I posted today and shared a copy of this document. So if you'd like a printable copy of all of the definitions, postulates, and axioms and propositions for Book 1, you can get that, and you'll see me using it here in our lessons from now on. Okay, so in Proposition 1.2, the task for us is laid out in the proposition, which is the first part of the proposition in general. Okay, and our proposition says to place at a given point a straight line equal to a given straight line. To place at a given point, so we're given a point, to place a straight line equal to a given straight line. So in this proposition, we're given a point and a straight line. And what we need to do is draw a second straight line at that given point, which is equal in length to the given straight line. Okay? To clarify our proposition, we're going to look at the exposition and determination. All right, the second and third part of a proposition. The exposition clarifies what's given to us in the proposition and prepares for our investigation, prepares for our construction and demonstration. All right, so in the exposition, we clarify what's given to us. We say, let A be the given point. So as the proposition said, we're given a point. Let's name that given point A. And you can see here that I've drawn on the board a point A. And remember what I said. We're contemplating a point named point A. This dot is not a point. This is a symbol of a point. What we're meditating on as we study geometry is a point. It has no length or breadth, just a point or a place. Okay? And we've labeled that place or point A. Let A be the given point, and let BC be the given straight line. And here you can see I've drawn a straight line with the endpoints BC. So this will be our given point, and this our given straight line. Now notice I've just sort of written this line BC kind of anywhere in any direction, and the point A, these can go anywhere. There's no need for these to be put in any certain place to work on this proposition. Okay, so I tried to make it look a little crazy by putting it on an angle like this, just to show you that the point and this line can be put anywhere, and the proposition will still be true and will still work out as it's going to work out. All right? So A is our given point, BC is our given straight line. In the determination, we clarify what's being sought in this proposition. All right? The exposition clarifies what is given to us in the proposition and prepares us for the work of the proposition. And the determination clarifies what we're going to seek in this proposition. It is required to place at point A a straight line that's equal to line BC. Okay? So the challenge of this proposition, what we're seeking, is to draw a line at point A that's equal in length to point BC. And remember, we're only allowed to use the elements of geometry to do so. Okay? So our proposition to review was to place at a given point a straight line equal to a given straight line. We clarified in the exposition what's given to us in this proposition. Let A be the given point, and let straight line BC be the given straight line. Third, in the determination, we clarified what's to be sought in this proposition. It is required to place at point A a straight line equal to BC. Okay? So we've laid out the challenge here of our proposition, and now it's time to move to the construction. What I've done here, I just want to clarify, in the construction and the demonstration, is I've written shorthand, shortened forms of what's written out in detail in your lesson. What I've written on the board here is really for my sake. Okay, so if you follow along, you'll understand what it says, but I've abbreviated it and used some symbols just to save some space on the board. But all of this is written out in detail in your printed lesson. Okay? Here we have the steps of the construction, and then we'll walk through the steps of the demonstration. I haven't drawn the construction on the board for this proposition because I want to do it as we go through the video so I can show you how to complete the construction. All right, so we'll get to work on that. We were given point A and a straight line BC, and our task is to draw a straight line at point A that's equal in length to the straight line BC. Here's how we're going to do it. First of all, we're going to draw the straight line AB by connecting point A and point B. Let me just move this label down a little bit. So we're going to connect point A and point B. We're allowed to do that based on postulate 1.1, which tells us that any two points can be connected with a straight line. So we're going to connect points A and point B to form straight line AB. That's our first step. Our second step of our construction is to construct an equilateral triangle named DAB, triangle DAB, on the straight line AB. So we're going to construct an equilateral triangle on the straight line AB. We can do that because we just proved in proposition 1.1 that it can be done and how it can be done. So we're going to do here in step 2 what we did in proposition 1.1 to construct an equilateral triangle. Okay? If you don't remember how we did that, let's walk through it. We had a given straight line, the line AB. And the first thing we did was we took point A as a center and point B as the distance to the circumference of a circle, and we drew a circle around center A at distance B. That was our first step. Then we took B as the center point of a circle at distance A and drew a circle about point B at distance A. We saw that those two circles intersected, and at that point where they intersected, we're going to label that point D. And then we're going to connect these lines, connect these points, DA and DB. In proposition 1.1, we said we're allowed to connect those points because of postulate 1.1. What we've now done is construct an equilateral triangle. And the proof that this is an equilateral triangle is provided in Proposition 1. Okay? You should remember what the proof was, but if you don't, you can go back and review Proposition 1.1 and see how we constructed an equilateral triangle and how we proved that it was in fact an equilateral triangle in Proposition 1.1. Okay? So we've completed step 2 here. We've constructed the equilateral triangle DAB on the straight line AB. Now, our third step is we're going to produce or carry forth line DA to produce line AE. So we're going to come from D through point A, extend that line, and we're going to say that this point is point E. So we've produced or extended line DA. We've extended it in a straight line to produce, you can either say line DE or AE. And we're allowed to do that based on postulate 1.2, which tells us we're allowed to extend the line to a point. We're going to do the same thing on line DB. We're going to extend line DB in a straight line, and we'll stick a point down here, and we'll label that point F. So we've produced straight line AE, and we've produced straight line BF. And postulate 1.2 allowed us to do that, all right? So we started with point A and straight line BC. We connected points A and B to form the straight line AB, and then we constructed an equilateral triangle DAB on line AB. We then extended line DA out to point E, and we extended line DB out to point F. All right, next, we're going to take point B as the center of a circle, and we're going to extend to distance C. So we're going to draw a circle from point B as the center with point C as the circumference of that circle, and we're going to draw that circle about point B like this. And where that circle intersects this line, we're going to label that point G. Okay? We're going to label point G where the circle at center B and distance C intersects line BF. And that gives us a new line, BG. Okay? And then fifth, we're going to start at point D, with point D as the center of a circle, and distance G, that's the point we just made using our circle from point B at distance C. That point where BC, that circle intersected BF, point G, we're now going to take this line from point D to point G and use that as the measure of our circle. And we're going to draw a circle around point D like that. And where that circle intersects line DE, we're going to label that point L. Okay? So point G here, just so this doesn't get confusing, point G is the point where the circle drawn from point B at the center to distance C intersects line BF. That gave us point G. We then used G as the distance from center D to draw another circle, and where that circle intersected line DE, we labeled that point L. Okay? Now, if you're paying attention, and if you're really sharp, you'll see that we just completed this proposition. We just did what was asked of us to do. Line AL here is a straight line drawn at point A that's equal to line BC. line AL is equal to line BC. So we've just done what was asked of us in this proposition. I want to say one note about these diagrams, okay? If you look at this diagram, the diagram is not drawn to scale, not drawn to scale. And what that means is the diagram is just a helpful illustration to help us visualize what we're thinking about or studying in this proposition. It's sort of a sketch. It's not an accurate drawing. And so we're not allowed to make any conclusions based on how this drawing appears, because the appearances are not true. What's true about this drawing is what we've said in our actual steps of our construction, or in the definitions, or in other points that we've made as we've formed this diagram. But to look at the diagram, we're not allowed to make any conclusions based on appearances, based on what things look like in the diagram. For example, line BC is actually, in our proposition, line BC is equal to line AL. Yet in our diagram, they don't look equal. But that doesn't matter, because the diagram is just an illustration, just a sketch. Okay, remember, I said in a previous lesson that a line would actually be invisible in geometry. A line has no width, so we wouldn't be able to see it. It would be a length with no width. We just draw a line as a symbol to help us in our contemplation. So it doesn't matter if our drawing is to scale, as we say. We understand what the drawing represents, and we don't make conclusions based on how our drawing looks. Sometimes when students don't know what they're doing in geometry, they'll look at a drawing, they'll look at the construction, and they'll try to guess things about the proposition based on how things look. But that's not part of geometry. The illustration, the diagram, is just a sketch to help us with our contemplation. Okay? So line BC, as we'll prove here in our demonstration, is equal in length to line AL. But they don't look equal in our diagram, and that doesn't matter. Okay? So don't let the diagram fool you, and don't get worried if your diagrams don't look perfect. They don't have to. Our conclusions are not based on the appearances of our diagram. Okay? Now we're going to prove that line AL is in fact equal to line BC. Okay? And remember, I've written things up on the board here in a shortened form for my own sake, and just to save board space, but everything's written in detail in your lesson. Okay? And I'll explain as we go through here so it's not confusing. So we have to prove now that line BC is equal to line AL. And remember, appearances in our diagram don't matter. That's not significant. So let's start our proof. Since point B was the center of circle CGH, and I didn't label point H on the construction, but you can see it in your lesson, okay? Since point B is the center of circle CGH, line BC is equal to line BG. And that's based on definition 1.15, which is the definition of a circle. Okay, the definition of a circle. The definition of a circle is that any point drawn from any straight line drawn from the center point straight to the circumference, any line drawn from the center to the circumference is equal to any other line drawn from the center point straight to the circumference. Okay? So the definition of a circle tells us that line BC is equal to line BG. Okay, that's our first point here. Point 2. Since point D was the center of the circle GKL that we drew. And again, I didn't label point K on here, but it's in your lesson. Since point D was the center of the circle GKL, then line DL, which is from point D to point L here, this line from D to L must be equal to line DG, because they're both straight lines drawn from the center of a circle to its circumference. So based on the definition of a circle, line DL and line DG must be equal to each other. And it says definition 1.15, which is the definition of a circle. Okay? Third point, line DA is equal to line DB. Here's line DA, here's line DB. These are two sides of the equilateral triangle that we constructed in the second step of our construction. We drew an equilateral triangle DAB on line AB. Since it's an equilateral triangle, by the definition of an equilateral triangle, the sides must be equal. Therefore, DA must be equal to DB, even if they don't look equal in our diagram. By definition, they're equal. Okay? By definition of an equilateral triangle, definition 1.23. All right, that's our third point. Point 4, AL must be equal to BG. AL must be equal to BG. And how do we prove that? Axiom 1.3. Axiom 1.3 is an axiom about subtraction. It says, if equals be subtracted from equals, the remainders are equal. If equals be subtracted from equals, the remainders are equal. So let's see what that means. The remainder AL is equal to BG. So AL and BG are called remainders here. DL is equal to DG, and DA is equal to DB. So if we subtract DA from DL, the remainder is AL. Think of it as a subtraction problem. DL is equal to DG. DA is equal to DB. If we subtract DA from DL, we're left with the remainder AL. If we subtract DB from DG, we're left with the remainder BG. Now, DL is equal to DG, and DA is equal to DB. Therefore, AL, the remainder, must be equal to BG, the remainder, based on axiom 1.3, that if we subtract equals from equals, the remainders must be equal. That's a self-evident truth. If you subtract two equal quantities from two equal quantities, the remainders must be equal. That's a self-evident truth. That's an axiom. Okay? So AL must be equal to BG. Okay, that's point 4. Now, point 5 here is just a reminder, because we already said in point 1 that BC is equal to BG. BC is equal to BG because they're both lines from the center to the circumference of the same circle. We're simply restating that here in point 5 as a reminder. And then we move on to point 6, that line AL is equal to line BC. You can see that here. AL equals BC. And the reference given for that point is Axiom 1.1, which says things which are equal to the same thing are also equal to one another. Things which are equal to the same thing are also equal to each other. AL equals BC. Well, what is it? What is the same thing? What is the same thing that AL and BC are both equal to? This tells us that AL and BC must both be equal to the same thing, and therefore they're equal to each other. What they're both equal to is BG. In point 4, we proved that AL equals BG. In point 1, we proved that BC equals BG. So AL and BC are both equal to BG. Okay, I'll say that again. In point 4, we proved that AL is equal to BG. AL is equal to BG. We proved that in point 4. We also proved that BC is equal to BG. We proved that in our first point. So AL and BC were both shown to be equal to BG. And therefore, based on Axiom 1.1, which says if two things are equal to the same thing, they're equal to each other, we can conclude that AL is equal to BC. And I'll just put a little line like this to show that this is equal in length to this. So we've proven here that line AL is equal to BC. And that's the challenge of our proposition. We've drawn a straight line at point A that's equal in length to the given line BC. And that's what we were to do. Okay? So, the last part of our proposition is the conclusion. And as I just said, it was required of us to place at point A a straight line equal to BC. We have placed the straight line AL at point A, and it's equal to BC. And we end our conclusion by restating that determination, clarifying that we've done what's required of us, and we conclude QEF, quod erat facendum, which means which was to be done. The conclusion, the detail of the conclusion is written in your printed lesson, but I'm just writing QEF to show that we've completed this proposition. So this here is the full solution to proposition 1.2. We were given a point A, and we were asked to construct a straight line at point A that was equal in length to a given straight line BC. Through the steps of our construction and through the steps of our demonstration, we've proven that this line AL that we've drawn here is in fact equal in length to the straight line BC, and it's drawn at point A, which was to be done. I know that's a lot of information, and we move through these steps quickly, but the reason I do that is to keep the videos as short as possible, and because I know that you can watch the video over again, you can pause it, rewind it, skip ahead, and so forth. So I hope that that's a helpful introduction. Walking you through this proposition. You can watch this video as many times as you'd like, but even more importantly, go and study the printed lesson where all of these things are written out in detail, and use the video and the printed lesson to help you study for mastery. I hope that's helpful. Proposition 1.2 in the Classical Liberal Arts Academy's Classical Geometry course. God bless your studies.